Hi everyone, this is Anushka and welcome back to my channel in Economist. So if you are someone who is following my lecture videos from quite a time, you will know in the previous few videos we have discussed about panel data, right? So we started off with the concept of panel data and then we have gone into the estimation process of the panel data. In the previous video, I have talked about this particular context, right? We started off with four different forms and we said we are observing them for 20 different time periods. If you haven't watched that video, please check that out. I will give the link in the description and also you will find that in the I tab button. So please check this out before going into this video. Otherwise, it will be difficult for you to understand this, right? So we have taken four different entities, 20 different periods, and we said we have 80 observations altogether, right? And on the basis of this particular data set, we have said there are five different methods, right? There are five different methods in which you can estimate this model. And in the very first video, that is the previous video, we have gone into this process and we have discussed in details what is method number one, which is also known as the pooled OLS regression. So where we have assumed that intercept and the slope coefficients, both intercept and the slope coefficients are constant across time and space. So this portion is done. Now today we will go into the method two. In method two, we will assume that the slopes are constant. Slopes are still not varying with individual entities and time periods, but we will modify this intercept parameter and we will say intercept will now vary over individual entities. Intercept still doesn't vary with time. It will only vary over individual entities, right? And if this is the scenario, then what will be the consequence of that? We will discuss this in today's video, right? So this is the agenda. Now let's straight away go to the model. So how will the model look like? The model will look like this. YIT is as usual our dependent variable. So now see the intercept, it will be beta 1i, or you could simply write it beta I also, beta 1i or beta I, whatever you want. So this I suffix will be there because we are introducing the individual specific heterogeneity, right? So beta 1i plus beta 2 x2it. Regressors are dependent on both entities and time periods, and see the slope coefficients are still constant. Then you have beta 3 x3it plus uit. So this is the model that we will work with for all I and t. This is the model. Now see beta 1i is the individual specific variation. Individual specific variation, and beta 2, beta 3, or let me write it, this is the intercept term, intercept coefficient that we already know from this model. And beta 2 and beta 3 that you see here, beta 2 and beta 3, they are constant. They are constant slope coefficients. They are constant slope coefficients. And the regressors that you see here, namely x2it and x3it, these are time varying regressors, right? They are dependent on both the entities and the time periods. Now, if you have this kind of model, this model is also known as the fixed effect model. Fixed effect model. This is very important to know. The previous model that we talked about, we called it as the pooled OLS model or pooled OLS regression model. Now, this kind of model that we study in method 2, where the slopes are constant, but the intercept varies over individual entity, this is known as fixed effect model. Why this is so? Because the fact that although the intercept term is varying over the forms that we can see from here, it varies over I, but each individual intercept does not vary with time. That is, it is time invariant. So let me write it down in short that each individual intercept does not vary with time. That is, it is time invariant. Time invariant. Right? So this is the reason it is known as the fixed effect model. So we are finding out the individual specific heterogeneity. So in our particular context, from this model, we can particularly know what will be the within variation of each of the entities, right? Within variation. It is also known as the within estimation model. Fixed effect model, also known as the within estimation model, right? Why do we call this so? Because we are trying to find out the time invariant, unobserved or observed heterogeneity across individuals or across entities, which is possible in the fixed effect model, which was previously not possible. In pooled OLS, we have said that this interceptum is also time invariant. Basically, uh, this was also a constant, right? Only beta 1. We have taken only beta 1. So in the previous case, this time varying heterogeneity cannot be found out, but this is the additional thing here which we can do. Now let's move forward and understand what is this fixed effect all about. So see, the fixed effect estimator controls for all the time invariant individual specific factors. It can be observed or it can be unobserved. So this is the main, advantage of this kind of a model, that we can capture all the time invariant individual specific factors, whether they are observed or they are unobserved, that may affect the dependent variable, that is yi. Dependent variable is, you can take it to be the production of each of the forms in our context. Now, these factors are eliminated by focusing only on within individual variation over time. So we'll see how to control this, how to estimate this kind of a model. We haven't gone into the estimation process yet. We will discuss two different methods in which you can estimate this particular model. So there I will discuss this within individual variation. Now see, it's ideal when do you use this model? This model is ideal when you suspect that unobserved characteristics like the ability or the productivity. So these are all the innate abilities that a person may have, which are usually unobserved, which you explicitly do not know, which you only encounter with time. Basically, if you work with someone, then you can discover that yes, this person has this particular ability, but previously it is unobserved. They may be correlated with the regressor. Suppose this ability is affecting the production of the form, right? It affects the dependent. It is very much possible that it will affect the dependent variable. If you want to find out what will be that effect, then only you can use this kind of a model, right? So basically, we are saying that covariance of the intercept term, suppose I call it beta I, and the regressors get correlated. Suppose this is the scenario. This is the assumption. The individuals intercept, the intercept term gets correlated with the explanatory variable, which will in turn affect the dependent variable. If this is the scenario, if you find this kind of a correlation is present, you will, blindly use the fixed effect model, because that will give you the most efficient answer, right? So here I have added this specific use cases. When do you use this model? When you want to control for unobserved heterogeneity across individuals. That is what we are discussing so far. We know in fixed effect model, unobserved heterogeneity is present. So if you want to control them, you want to tackle them or handle them, which we will see how we can do that. So in that case, you will use the fixed effect model. The second thing, when those unobserved factors may get correlated with the regressor, which means basically this. The unobserved factors get correlated with the regressor. If this is the scenario, then also you will use the fixed effect model. And the third thing is that when your interest is in how the changes within individuals affect the outcome, right? Within individual effects cannot be found out in the pooled OLS, but it can definitely be found out in the fixed effect model. That is why if you are interested in that, then also you can use this fixed effect model. I hope this much is all right. I have added certain advantages and disadvantages also. Advantage is that it eliminates, before going into estimation, we will see, we will eliminate. So control for me, we want to basically eliminate this time invariant effects, right? We want to eliminate all sorts of time invariant effects, because that will give us a fixed effect. Fixed effect means the effect that we want to find out after eliminating all the time varying factors, basically time invariant factors, basically. So that is what we will do. So it eliminates all the time invariant omitted variables that may vary across individuals. It provides unbiased estimates of the slope parameters, even if alpha I, or the basically the variations that we have talked about, they are correlated with the regressors, and it is useful for policy evaluation, panel experiments, and causal inference. Now, there are certain severe disadvantages also of this method. It cannot estimate coefficients of time invariant variables. Suppose you enter these variables in your model. Suppose gender. Gender is a qualitative variable. It doesn't vary with time, right? Gender is a qualitative variable. So basically, you have to treat this with dummy variable. So if these kind of variables are present in your model, which are time invariant in nature, then their coefficients cannot be estimated. This is one of the severe drawbacks. Now, the second thing is that it reduces variation only within variation, not across variation, only within variations can be handled. Now, third is it is sensitive to measurement error. And the fourth, this is also a very severe disadvantage, is that it may inflate the standard errors. Why this is so? Because we will use different dummy variables. We'll see just now that how to estimate that. We will see, we will introduce certain dummy variables to handle this situation that will in turn reduce the degrees of freedom. So these are certain advantages and disadvantages. You can take a look at this. And this is for the coding purposes. If you want to code this, if you want to import your own data set and you want to try this, you can do that. I have added the Stata code here and the Python code here. In this video, I'm not going into coding. I will make a separate playlist. There I'll explain this in detail. So as of now, if you are interested, you can take a screenshot, you can pause the video and see how to perform this, right? Now, we will start with the estimation process, right? Panel data estimation, fixed effect estimation, basically. How do you do that? So, as I have told you, there are two different methods. There are two different methods in which you can perform this. The first method is known as least square dummy variable model, dummy variable method. Least square dummy variable method. And the second method that you have, let me use another color. This is known as the time d-mean estimator, or which you also call the within estimation. So now we will discuss each of them. What is time d-mean estimation and what is the least square dummy variable method? Let us start with this method, which is the least square dummy variable method. Here, what you have to do, as I have told you, before going into estimation, before doing any kind of operation, what you have to do, firstly, you have to eliminate. Either you have to completely eliminate or you have to, modify your time invariant factor. What is the time invariant factor you have? Beta 1. So see the model once. The model is this. So this is the only time invariant factor here. So somehow you have to treat this particular portion. You have to control for, you have to handle, you have to modify this portion so that we can handle it better. So let us see how do you do that. So here in the first method here, we shall introduce dummy variables. The name is least square dummy variable method. So you have to introduce certain dummy variables and consider the model as. Consider the model as follows. So the model will look something like this. YIT, this remains as it is. Then instead of beta 1i, what you do? Firstly, introduce a common term, constant, basically an intercept term, alpha 1 plus for 4 different entities. Remember that we are talking about 4 different firms. So we have 4 different entities. In order to avoid the dummy variable trap, we will only introduce 3 dummy variables, right? Dummy variable trap, dummy variables we have discussed in our econometrics playlist. Again, I'll give the link in the description. If you are new to this, please check this out. So the model will look something like this. Alpha 2 D2I, alpha 3 D3I, plus alpha 4 D4I, plus the rest of the terms are as it is. Beta 2 X2IT, plus beta 3 X3IT, plus UIT for all I and T. This will be the new model that you have to work with. So this side remains the same, dependent variable remains the same. Now alpha 1, we have introduced a common intercept term. And then we have introduced three different dummy variables. As I've told you, for four different entities, you have to introduce only three different dummies. So if you are talking about n in general, if you have n different entities that you are talking about, then you have to introduce n minus 1 different dummy variables in the model. So see, this portion, we have just modified our time invariant factor. Can you observe this? This is the entire thing. Let me remove this. Yeah, see now. This is the thing. Instead of writing the time invariant intercept factor, intercept parameter, we have introduced this particular thing. Why we have done this? Because if you have this time invariant factor, you cannot find out fixed effect. For finding out fixed effect, you have to first control for the time invariant factor. That is why we have to use this step, right? So alpha 1 plus alpha 2 D2I plus alpha 3 D3I plus alpha 4 D4I, and then we will estimate this particular model where we assume that this D2I will take the value 1 when, if the observations, let me write in short, observations, this is observations belongs to the first form. If the observations are belonging to the first form, which is the form number A, and it will take the value 0 otherwise. In the similar way, we will do for D3I as well. D3I, we will assume that it will take the value 1 if the observations are belonging to the second form, which is form number B, and it will take the value 0 otherwise. And similarly, for D4I, it will take the value 1 if the observations are belonging to the third form, which is the C form, and 0 otherwise, right? So this is the thing. Now, if you have this, what we can say, sure, no dummy variable is introduced for the fourth form, which is the form D in our context. So it is called, if you remember, we have discussed this in our dummy variable video also. This is known as the benchmark category, or comparison category. Benchmark or comparison category. So basically, we will compare the other form's production with this particular form. So form D will be the benchmark category, and we will do all the comparison, because basically we will compare the form D's production is the benchmark. We will compare this production with the A form's production, with the B form's production, and with the C form's production. So this is basically the base, on the basis of which we are measuring, or we are comparing, or we are judging the estimate, the production of all the different forms. That is why we do not need to introduce another dummy variable, right? So this is the thing which we use for avoiding the dummy variable trap. So specifically, if you see, the model is like this. The model is this. So if you want to basically explain what will be the interpretation of all these things, can you do that? Can you pause the video and think what will be the interpretation? This also I have taught you in the dummy variable video, how to estimate, how to interpret this, not estimate, how to interpret this thing. So alpha 1 will be the common intercept. Alpha 1 is the common intercept. Which basically gives you the performance of the benchmark category, or let me write of the dth form basically. Then alpha 2 will be what? Alpha 2 will be the difference in the production of the first form and the dth form. What is alpha 3? Alpha 3 will be the difference between the second form and the dth form. And alpha 4 will be the difference between C and the D form. So this will be the interpretation. If you want to interpret this thing, alpha 1 is the benchmark category. So overall, this will give you the overall effect basically. Overall effect or the benchmark performance. This will be given by alpha 1. Then you have alpha 2. Alpha 2 will give you the difference between the second form, that is the Dth form, and the benchmark category basically. So B minus D, which I have written here. And then you have alpha 3 and alpha 4. So this is how you have to interpret all of the coefficients, right? Now, since we are using dummy variables, to estimate the fixed effect model. Fixed effect model, I'm writing in short, fixed effect model. This method is called least squares dummy variable model, in short LSDV. So in many question papers I have seen, they have only given you this short form. What is LSDV? So you have to identify where we are talking about this method, least square dummy variable model. This is also known as, so see, since we are using dummy variables to estimate this fixed effect method, that is why this model is known as the least square dummy variable model. It has an alternative name also. It is also known as the covariance model. So it's better to know the alternative terms also, where x2 and x3 are covariates. There is another term for this. It is also known as the unrestricted model. This model is known as the unrestricted model. Why this is unrestricted? Because I can vary. I basically represents the entities, right? I basically are the different entities, that is the different forms that we have taken under consideration. So since, let me write, I varies. The reason is this. That is why it is known as the unrestricted model, because I can vary across different forms or different entities that you are taking under consideration. This term will be very important, because see, this will help us to judge which model to use in which cases, right? So remember that this model, that least square dummy variable model, this particular model that we have estimated, let me call it 2, model number 2. And let us assume that the pooled OLS regression, remember in the first video we have discussed the pooled OLS regression model. Let me go back and show you what we have done earlier. Okay. So this is the note from the previous video. Let me show you the model. Suppose this is the pooled OLS model, which we call as number 1. This model is known as the restricted model. Why this is restricted? Because it cannot vary. The intercept parameters and the slope parameters cannot vary across entities and across time, right? This will serve as the restriction. You have to follow this thing. Restriction means you have to follow certain rules. That is the restriction. Restriction is that this beta 1, beta 2, and beta 3, it cannot vary across time and across individuals. That is the restriction. This model, this is the first model, which is known as the restricted model. Here, how many parameters are there? Three parameters, beta 1, beta 2, beta 3. These three are the constant parameters. Now, let us go back to our new model here. This is the model we are currently talking about. So here, how many restrictions are there? How many parameters that you want to estimate? 1, 2, 3, 4, 5, 6. So here you have six number of parameters, but that is why the degrees of freedom will be lower. Remember in disadvantage, I have told you the degrees of freedom will be lower in this model. Let us see now. Now what we will do, we will test whether our pooled OLS regression was better or this unrestricted model is better. Right? A model is only successful if it gives you, favorable results. Basically, the answers improve basically. So in order to test that, what you have to do, you have to run a F test. Basically, we will do the hypothesis testing now. We will test, let me write testing of hypothesis. We will try to find out which model is better. Which model is better? What is the criteria for that? We can use a formal test to evaluate the performance of model 1 and model 2 by using restricted F test. Restricted F test. What is this restricted F test? Here, the statistic will look something like this. Here, the F statistic will be this. F will be R square that you will get from the unrestricted model minus R square that you will get from the restricted model upon, we will have to write number of restrictions. Number of restrictions in the first model basically. So in 1 upon 1 minus R square, the unrestricted model, upon n. N is the total number of observations, that is 80 in our purposes, minus the parameters in the unrestricted model. In say model 2, in model number 2. Specifically, we call this thing as V1. That is the degrees of freedom. Remember that in F test, we take the ratio of two different chi-square variables and we divide them by the respective degrees of freedom. So this will be V1 and this will be V2. So number of restrictions in the model 1 will be given by V1 and the n minus the number of restriction in model 2, this will be given by V2 and this under each node will follow F distribution with V1, V2 degrees of freedom, right? V1, V2, let me write it again. This will be V1, V2 degrees of freedom. I hope this much is clear. Now, in our purposes, we do not know what is the R square. So, R square of the unrestricted will be there. R square of the restricted model will be there. Now, what is the number of restriction in model 1? We just showed you beta 1, beta 2, beta 3. 3 restrictions are there. So, you have to divide this thing by 3. And 1 minus R square unrestricted. We do not know this R square. You have to find that out. This will be 80 minus n minus the number of parameters in the model number 2. Here you have six things, right? 6. So it will be basically 74. So it will be basically following F distribution with 3 and 74 degrees of freedom. Now, how do you decide which model is better or not? For that, you have to follow this decision rule. The rule is if F is greater than F alpha V1, V2, then you will say you will reject H naught. H naught is rejected. That is the restricted model or restricted regression model will be valid. sorry, restricted model will be invalid. That implies that we need to switch to model number 2, right? So this is the entire process of the least square dummy variable method. I know I have gone into a lot more details. Many of you don't, need this much details, specifically if you are in your undergraduate courses. But still, I wanted to give you a flavor of what we are doing. That is why I have added this thing. So this will give you a flavor that which model to use in which case, right? Whether you should use the pooled regression model or you should use the fixed effect model in terms of least square dummy variable method. This particular test using the F restricted F test, you can find that out. So this is how you do the first method, that is the least square dummy variable method. This is done. The only small thing that is left is time demeaning estimator or the within estimator. Let me quickly show you this and then we will stop for this thing. Right, for this, you have to again start with the model that we had initially. So this is method number 2 that we are talking about. So our original model was this. Let me write it down. X2IT plus beta 3x3IT plus UIT. Now in this model, so in the second method, basically, not the model, in the second method, what you have to do, basically, we are trying to completely eliminate this factor. We are trying to completely control means elimination. In the previous case, what we have done? In the previous case, we just introduce certain dummy variables to modify this thing. Right? Certain dummy variables were introduced to modify this thing. But here, what we do in this particular method, in the time demeaning factor or within estimation method, we will completely eliminate this. How will you do that? You will take the average of this entire equation over t. So let us first do that. If you take the average or take the average of this equation over t for all I. Across all individuals, you will do that. Once you do that, the first thing will be this. If you take the average, the left hand side will be this. Then this beta 1I will be as it is. Then you have beta 2 x2 bar. Then you have beta 3 x3 bar. And then you have u bar. Or you can write ui I bar, basically. Now what you have to do, simply take this, let me call this star, and let me call this equation double star. You will simply do star minus double star. If you do that on the left hand side, you will have this yi minus y bar. This beta 1, see this beta 1i will get eliminated, completely eliminated if you take this, difference. So it will be x2it minus x2 bar plus beta 3 x3it minus x3 bar plus uit minus ui bar for all I. Can you see this? Now again, what you can do, you can write it in the deviation form. Remember, this is the deviation form. So let me show you that. So simply first term will be small yit, then you have beta 2, small x2it plus beta 3, small x3it plus, let me call this uit minus ui bar, let me call this small vit, right? So this is the reduced model that you have to use for the time, demeaning process. And this model is known as within transformation model. This is known as within transformation model, where YIT, this YIT is known as the time demeaned data. Time demeaned data on Y, on small y basically. So basically what we are doing, we are, taking the mean. We are taking the mean, and that is how we are eliminating the effect of time. If you take the average over time, you are removing the effect on that, right? You are saying across time. Basically, you are eliminating, you are taking out the power from the time. So that is what we are doing here. We are demeaning the time demeaned effect. This is known. So XIT is the time demeaned data on X, and VIT is the time demeaned error term. Is the time demeaned error term. Also, if you look at this, how we have taken this average, let me show you. Average will be averages that we have done. So yi bar, we have simply done 1 upon t, summation t from 1 to t, yit. This is how we have taken this average. And xi bars, all the regressions that we have done, this is simply I from 1 to t, xit, and ui bar that we have got, this is simply taking the average of the idiosyncratic error term, uit. So see, on the left hand side, you only have I. So that is the point, that if you take the average with respect to t, where t is varying, sorry, this will be t, this will be t, this will be t. So if you take the average with respect to t, when this t is varying over across all the time periods, that is from 1 to t, then you are basically removing the effect of t. Can you understand this thing? I know it might seem a little hard, but this is how the things are here. Right? If you have any questions, you can let me know in the comment box. I'll reply to that. So we are taking this average. Basically, what was our aim? We have started with the aim that we have to control for the unobserved heterogeneity, right? Unobserved heterogeneity, time invariant heterogeneity. So basically, we have to neutralize the effect of time. That is why we are doing several methods. We have done two methods as of now. First method is that simply introduce dummy variables and then handle that. And the second method that we have done is that we are just completely eliminating the time invariant effect. How we are doing this? We are doing the average. We are time demeaning the process. We are using the time demeaning data. We are transforming the model, which is also known as the Boolean transformation. We are essentially transforming the model by demeaning the time, by demeaning the y variable, demeaning the x variables, and also demeaning the error terms, the stochastic error terms. We are demeaning all of it. That is how we are controlling for the time invariant effects, right? Now, if this is the model, then see, this is known as the Boolean transformation, this fixed effect transformation. Let me write it. Okay, let me write it here. The fixed effect transformation is also called Boolean transformation. Within transformation. So basically, we are not doing across transformation, we are doing within transformation. This is known as the within transformation process. We are controlling for the individual time varying things. And since the unobserved effect has disappeared, let me call beta 1i, this is the unobserved heterogeneity basically. This has completely disappeared. This has completely disappeared. We can estimate, we can use pooled OLS now. Pooled OLS to estimate the model, to estimate this particular model. So see here, if you are able to eliminate that, then your model has just become the pooled OLS model that we have started off with the previous video, right? If you have this kind of a model, this is a transformed model. This is the within transformed model. We have done this by taking the averages and then subtracting the things. This is the process. We have done this, right? So we have completely neutralized the effect of this time varying factor, and we have landed up to this within transformation model. Now, if you apply pooled OLS on this within transformation model, then your result will be efficient. So this is how you are handling the heterogeneity. You are controlling for the time invariant heterogeneity. I hope this process is clear to you. So we will work with this within transformation. How will you estimate this model? Now, in this within transformation model, if you know, if you apply the pooled OLS method, see here, if you apply the pooled OLS method here, then you will again get efficient estimates. So in other words, a pooled OLS, a pooled OLS estimator, a pooled OLS estimator based on time demeaned variable, time demeaned variable is called fixed effect estimator, right? So this is the entire thing that I wanted to share with you. This is very important for you to understand. Again, I am saying, if you have any questions anyhow, you can definitely let me know. You can write it directly in the comment section. I'll reply to that. So the pooled OLS estimator, which is based on this time domain variable, is known as fixed effect estimator. And just one quick point, just the finishing thing that I wanted to tell you is how the degrees of freedom will vary across different methods. So we have so far done 3 different methods. First is the pool OLS method that we have done. Then we have gone into the fixed effect method with time demeaning thing. This we have studied today, time demean. And then we have gone into the least square dummy variable model. So these are the 3 models that we have discussed so far. Now I wanted to, I want you to pause this video and think about how will the degrees of freedom change in these 3 different models. So for the pool OLS model, if you remember the pool OLS model, the degrees of freedom will be, the general formula is what? General formula is total number of observations minus the total number of parameters estimated. So in case of pool regression, the total observation will be NT, that is 80. In our case, this is 80 because remember we have 4 different entities and uh, you know 20 different time points. That is why it will be NT. NT minus number of parameter estimate is basically K, is denoted as K. So in general, NT minus K will be the degrees of freedom in the pool OLS version. Now, interesting thing happens in the fixed effect in the time demeaning case. In the time demeaning case, this total number of observations remains the same. The total parameters also remains the same. But here you have to additionally subtract one N. Why this is so? Because you will lose 1 degrees of freedom per entity, right? You will lose 1 degree of freedom per entity due to the entity specific intercept. That is the fixed effect. Due to fixed effect, because remember that for beta 1i. So for all I when it will vary with A, B, C, D, this intercept term will vary. Right, this intercept term will vary. So for 4 different entities, you will lose 4 degrees of freedom. For every entity, you will lose 1 degree of freedom. For every entity, you will lose 1 degrees of freedom. In general, if you have n different entities, then you will lose another n different degrees of freedom. Right? For every equation, so if you write the equation, first equation will be beta 1a, and then the rest of the thing. In the next equation, it will be beta 1b and then the rest of the equations. So it will be in the similar fashion, beta 1c and beta 1d. So these are 4 different restrictions that you are introducing additionally in your model. That is why this additional n has to be subtracted, which is very important for you to understand. This is extra here. This is extra here. Now, what will happen in case of least square dummy variable? In least square dummy variable, we include dummy variables for n minus 1 entities, right? Dummy is introduced for n minus 1 different entities. So what will be the degrees of freedom? Degrees of freedom will be NT remains the same, total observations. Now for n minus 1 different dummies, n minus 1 different restrictions will be imposed. minus the total, the number of regressors. Number of regressor will be k minus 1. Number of regressor is k minus 1. We are not computing, we are not taking into account the intercept because the intercept is changed now. Right? Remember, in case of least square dummy variable, we have modified the intercept only. We have introduced n minus 1 different dummy variables instead of the intercept. So now you only have k minus 1 regressors. Right? You only have k minus 1 regressors. We are just computing them differently. And now if you simplify this, it will be nt minus k minus n only. So what you can say from here is that both the fixed effect time diminishing model and the least square dummy variable model has the same degrees of freedom. See, nt minus k minus n, here also you have nt minus k minus n. So this fixed effect model and the fixed effect time diminishing method and the least square dummy variable method, they will both give you the same degrees of freedom, but just they are computed differently. That is the only thing that you have to know, right? So yeah, thank you so much for your time. This is all I wanted to know. We have finished completely method 1 and method 2 of estimation of the panel data. I hope you like this video and this is of immense help of you. I know many students who struggle to get these concepts. I know they are a little hard, but if you have any questions, I have tried my best to explain you in the best possible way. Still, if you have any questions, please let me know. I'll be more than happy to answer that. And if you like this endeavor, please do the like button and do subscribe to this channel in Economist because this will give me immense motivation to continue making these useful videos for you. It takes a lot of time and effort from my side to make these videos every single week. I try to post 2 to 3 videos every single week for you so that you get the benefit of this. So if you think that this video is helping you in scoring better, in grasping these concepts better, then please support my endeavor. Do hit the like button and help my channel to grow, right? So thank you so much for your time and let's meet you in the next video where we will discuss the rest of the methods. Thank you so much.